Good morning. Today, thanks to my dentist visit, I'm going to present the two horrible examples I was going to look at in class today. Hopefully, this will make it a little bit easier to understand. One of our course objectives is to learn to read and interpret mathematical material. In this problem, the region of the first quadrant below the graph y = 9 minus x squared is revolved about the vertical line x = 5. What is the volume of the resulting three-dimensional solid shape? To be able to interpret what we're supposed to do, we have to take each one of these things separately. In the first quadrant means neither x nor y can be negative. That means we're only interested in the part of the graph that's above the x-axis and to the right of the y-axis. But not only that, I want to take only the points that are below the graph of y = 9 minus x squared, which are also in the first quadrant. Y = 9 minus x squared is a downward opening parabola. Highest spot is at x = 0, y = 9, and cuts across the x-axis at x = -3 and at x = 3. The points that are in the first quadrant, which are below the graph of this parabola, need to be like that and like that. The region that's described in the sentences is this shaded in region. I want to revolve this region about the vertical line x = 5 and think about the resulting three-dimensional shape. On the far outside of it, it'll be flat and vertical. The bottom will be horizontal as I go from as far away from x = 5 to as close as x = 5 as I can manage. This has varying distances from x = 5. We'll have to do something about that. The point here is only these shaded in points are the points that are going to matter to me. If I imagine taking the region and doing as we said, every point in the region goes around in a circle centered at x = 5. I'm going to get a shape that looks like this. It's going to be a chunk of a cylinder with a curved piece carved out of the middle of it. The reason that there's a gap here is there's a gap between the axis of rotation and the rightmost points that actually contribute anything. Here, I'm only drawing in things that are relevant to me. I'm not revolving around either the x or y axis, but I am revolving around an axis parallel to the y-axis. That suggests that I should chop the collection of y numbers up into smaller pieces. Doing so, think about the points that I'm going to revolve around x = 5 that go with one of the subintervals in the y direction. I'll call the extent of that delta y number I. Within that, I'm going to select a representative y value, c number I. This distance is the x-coordinate that goes with y = ci on the graph of y = 9 minus x squared. This x-coordinate is always 0. If it were not for this gap, if this strip extended all the way to the axis of rotation, then when I revolve this about the vertical line x = 5, this would sweep out a disk from x = 5 to here, x = 5 to there, x = 5 to an equivalent distance in the right direction, that you went in the left direction. However, life is not that easy. There is a gap here, so I'm going to have to leave some stuff near the center out. This distance is, as we've already mentioned, the horizontal distance from the vertical line x equal 5 to the y-axis. That is always 5 minus 0. This is the big radius of my washer. On the other hand, the piece that I have to leave out, the piece that's associated with this gap, is going to have a radius that varies as the point varies that we're looking at. Close down here to the bottom, it's very nearly equal to 5 minus 3. Up near the top, it's 5 minus a number that's not as big as 3. The inner radius, which we said a minute ago, was going to be 5 minus the x-coordinate of the spot that goes with, needs to be figured out. This is not a big problem, though. If y is equal to ci, and we're on the graph of the parabola, y equal 9 minus x squared, ci must be 9 minus x squared, and it's very direct to figure out that x must be plus or minus radical 9 minus ci. Since we're in the first quadrant, we don't want any negative coordinates, so that tells me that the relevant x here is square root of 9 minus ci. The small radius is the horizontal distance from x equal 5 to x equals that, where that is square root of 9 minus ci. So by this point, we've identified what we're going to call the perpendicular height, delta y number I. We've identified the large radius, which is always 5 in this case. We've done some algebra and figured out that the small radius must be 5 minus radical 9 minus ci, where ci is a representative y value in the one particular chunk that we're thinking about right now. So magnifying the picture and turning it so that I'm just thinking about it in terms of the geometry, the perpendicular height is delta y number I. The big radius, the distance from the axis of rotation as far out as you can get, is always 5. The small radius depends on the y-coordinate that you're using. The small radius is 5 minus radical 9 minus ci. So we know the big radius, the small radius, and the perpendicular height. Using our recipe, pi multiplied by big radius squared minus small radius squared multiplied by perpendicular height gives us this as our estimate for the volume of chunk number I. Notice I put some brackets in. I really need those brackets. 5 squared by itself is not a problem. I have to square the difference of 5 minus radical 9 minus ci. I don't want to goof the order of operations up. Once I've done that, whatever results needs to get multiplied by pi and also multiplied by delta y number I to give me what I've figured out here. There will be some algebra to do. I can either do it now or just leave it as is for the moment and do it once I've expressed this as an integral. Once you've done that, to get the exact volume, you take the limit of these sums as all of the delta y's tend to 0. However, we've played this game a number of times by now. Limit of the sum of something that involves ci times delta something turns into an integral, provided, of course, that the ci are y values out of each individual subinterval. So limit of sum, integral sign, delta variable name number I, d variable number name, ci turns into the name of the variable. This is the integral that we have to calculate in order to answer the question. So at this stage, all of the hard work is done. All we have to do is do the integral. There's going to be some algebra to do, and I want to be extremely careful about this. This number is 25. I'm going to subtract something away from that. The thing that I'm going to subtract away is the square of 5 minus radical 9 minus y. It's this quantity that I have to subtract away from 25. So I'm going to be careful about my plus and minus signs here. I need to integrate pi multiplied by 25 minus that, the square of 5 minus radical 9 minus y. When we figured that square out, it was 25 minus 10 radical 9 minus y plus 9 minus y. Now I'm going to drop the innermost brackets, but because of this negative sign, I have to remember to reverse the sign on each one of these terms. There is some good news. The 25s cancel out. That's it. That's the good news. This isn't, though, really as bad as it looks at first. If y is the variable, an antiderivative for y minus 9 will be easy enough to get. The only other issue is an antiderivative of 10 radical 9 minus y. I can go after this in one of two different ways. I can split it up into pieces and then deal with each piece separately, or I could just deal with the one big whole thing. Looking at the radicals, I believe that that first idea is more appealing. So we will deal with that by itself, and then after that, do something with this. Add the two results together and multiply by pi. Doing the integral with the antiderivative method, we get a result of negative 81 over 2. At first glance, that seems kind of strange because we're calculating a volume. It isn't, though. This individual integral is one of two different things I have to combine to get the volume. Y minus 9 is negative on the interval between y equals 0 to y equals 9. This integral should be negative, and in fact, it is. This is the other integral that I need to know. I could go after this two different ways. First, I could make a substitution, find an antiderivative, re-express that back in terms of y, and then put y equals 0 and y equals 9 into the antiderivative. Or I could make a substitution, but do it sort of completely, even including the limits of integration. For variety, I'm going to do it that second way. I'll let u equal 9 minus y, so the derivative of u with respect to y is negative 1. Abusing the language in the standard way, du is negative 1 times dy, meaning that dy is negative 1 times du. The limits of integration are y equals 0 and y equals 9, which correspond respectively to u equals 9 and u equals 0. we've got to be careful we don't get these in the wrong order here. The lower limit of integration corresponds to y equals 0. The lower limit of integration corresponds to u being 9. The upper limit of integration corresponds to y being 9, which makes u equal to 0. Putting all these pieces together, I have to calculate the integral from 9 to 0 of 10 radical u times negative 1 du. This looks very strange at first. If I bring the factor of negative 1 out front, and remember that when I interchange the limits of integration on a definite integral, the integral simply flips a sign, the thing that I have to calculate now becomes the integral from 0 to 9 of 10 radical u du. This integrand is positive on the interval from 0 to 9. This integral, despite the appearance of this, will end up being positive. Putting the numbers in, this second integral is 20 over 3 times 9 raised to the 3/2 power. I'll go ahead and simplify that a little bit more. So, taking care of the arithmetic, the second integral works out to be 180. Putting all of this back together, I end up with 279 pi over 2. I double-checked this using some techniques from numerical analysis, and it certainly looks as though that answer is right. This is the volume of the three-dimensional solid that we were talking about. In this particular situation, the calculations were rather involved. There were about 1 million places that we could have made a mistake, but it looks as though things worked out all right. Even so, this is pretty horrible. This is all I'm going to talk about in this particular video. Coming up next, we'll see that even though this was horrible, it's not as bad as it could have been. But I'm going to stop right there. I hope everybody has a good day, and I'll talk to you again soon.